Thank you for joining me as we go through and we try to prove a new theorem, and that is we're going to say that if a is an integer, then if 10 does not divide a, then 2 does not divide a, or 5 does not divide a. And as we prove this, we're going to do this by using a proof by contrapositive, and we're going to be able to use only our definitions and the lemma that if 2 divides a times b, then 2 divides a or 2 divides b. So we'll be able to assume this, but we'll have to show that this theorem is true using a proof by contrapositive. Now, as we did last time, we're going to go ahead and write this theorem using symbolic logic first so that we can figure out exactly what it's stating and what we have to prove. So in this case, what we have is that a is my variable. So I'm going to say for a is an integer, so variable a is in z. Then what I have are the statements 10 does not divide a, 5 does not divide a, and 2 does not divide a. And so actually I'm going to write P of a is 10 does divide a, and Q of a is 5 does divide a, and R of a will be 2 does divide a. And so what I want to do is I want to connect these statements using my connective so that I get out this original theorem. So now if we look at this, we're going to say for a and z, and so that's assuming that this is going to work for all integers a. So what we're going to have is for all integers a, we have that if this, then this. So we're combining this with an if then. The if part is going to be my P of a, so if P of a, except it's going to be a not, so it's if not P of a, because remember P of a is 10 divides a, but up here we have 10 does not divide a, so we're going to have the negation of P of a if that. Then, and now I have to figure out how to write this statement. So I'm going to take that one step at a time, and I'm going to say, okay, 5 does not divide a is the negation of Q, so that's going to be not Q of a. And then we're connecting with an or, so I'm going to say or, and then 2 does not divide a is the negation of R of a, which is 2 divides a, so we get not R of a. Therefore, what we want to show is that for all a and z, if not P of a, then not Q of a, or not R of a. Now that we have our theorem written out in symbolic logic, what we want to do is we want to remember that we're going to use a proof by contrapositive. So therefore we should actually write out the contrapositive. And so what is that is the contrapositive in general is if I have if P then Q, the contrapositive will be if not Q, then not P. So in this case what I want to do is I want to switch the Q's and P's and I want to negate them. So I'm going to get for all A and Z, not 5 divides A, or not 2 divides A. So if that, then not 10 divides A. So now I've rewritten this using the contrapositive, and what I want to do is I actually want to simplify this so I don't have to worry about so many negations floating around. So then if I negate an or, I get that that's going to be the and, where I negate each statement. So I get not 5 divides A, and not 2 divides A, if that, then, and now I'm going to go ahead and simplify this. The negation of the negation is just the original, so not is the original, so I get 10 divides A. I'm going to use that same trick again to simplify this one more time, and so I get for all A and Z, not is just the original, so 5 divides A and 2 divides A, then 10 divides A. So by trying to prove the contrapositive, where these are equivalent statements, we know that if this is true, if and only if this is true. So if I prove this, I've proven this. And so I've rewritten it so that it now looks like, okay, for all A and Z, we have that. If 5 divides A and 2 divides A, then 10 divides A. And so this is now the proof that we're going to try to do, and we'll use a direct proof on this one. That is, we'll assume this, and we'll show this. The next thing we want to do is we're going to write down any definitions that we're going to need, so anything that was used in the theorem. And so we have for all a and z, so we want to talk about what was z again. Well, z is the set of integers. So what we're going to say is that a is in the set of integers, or a is an integer. So that means a is a positive, negative, or negative whole number, or 0. So when we look at a, we know that it can be any positive or negative whole number, or it can be 0. But it will be an integer, and so we want to keep that in mind as we work through. The next thing we had was we had this divide thing again that we saw last time. Was we say that a divides b if b is equal to a times k for some integer k. Now, those were the only things that worked their way into this theorem, aside from ands and ors and ifs and thens as their connectives. So we really just need to know, okay, the set of integers is this set of numbers, and if a divides b, we can rewrite it like this. And so we'll use those as we go through and try to prove this theorem. Now that we've gone through and we've written down our definitions and written our theorem in symbolic logic, what we're going to do is say, well, what is given to us, what can we assume, and then what can we show, or what do we have to show. And so in the process, I'm going to write equivalent statements over here and over here and try to find some way to connect these. So the first thing I would notice is that 5 divides a, which means that a is equal to 5 times some integer, we'll say k1, and a is equal to 2 times some integer k2, so I'm going to say 4 k1 and k2 in the set of integers. In the same way, I'm going to go over here and say, well, if 10 divides a, that means that a is equal to 10 times, I think I'm up to 3, so k3, for some integer k3. So now what I have to do is I have to think about, well, how can I get from over here to over here? So that is, can I show a is equal to 10 times some integer? Now, if I'm looking at this, I start to pick up and say, okay, well, if it's 5 times some integer and 2 times some integer, somehow I want to get this so that I can write 5 times 2 to get out 10 times some integer. And so what I have to think is, well, how can I do that? Well, what's going to happen here is notice that because 2 divides a, 2 divides a, which is 5 times k1, so 2 will divide the product of 5 and k1. Now, we notice that 5 is odd. So if 5 is odd, and we multiply by an odd number, we're going to end up with an odd number. So that means that k1 will have to be even. So 2 divides k1. What that means is that k1 is in fact equal to 2 times, and then come up to k4 for some integer k4. Now, if I combine that together, what I get is a is equal to 5 times k1, which is equal to 5 times 2 times k4, because k1 is indeed equal to 2k4, so what we get is a is equal to 5 times 2 times k4, but that is 10 times k4. And since we wanted to show as 10 times some integer, we just let that integer be that k4 we were talking about. And actually now we have what we want. Notice that there was a step in here that we had to show that this implied that k1 was even. So we're going to have to include in our write-up some type of way to show that if 2 divides 5 times k1, then 2 has to divide k1. So now let's go ahead and combine this all together and write up a formal proof. Now that we've combined all that information together, we're ready to turn this into a proof. So what I'm going to start with is I'm going to say what I'm assuming. So let a be an integer. And suppose that 2 divides a and 5 divides a. So now we're assuming the negation of the then part so that we can do a proof by contrapositive. So we have a is an integer and 2 divides a and 5 divides a. So what did that mean is then A is equal to 5 times K1 for some integer K1, and that follows by definition because 5 divides A. So we know that A is equal to 5 times K1. Now, furthermore, we noted that 2 divides A, which is equal to 5 times K1. So 2 divides 5 times K1. Now, what we said was that, okay, well, 2 divides 5 times K1, so therefore K1 would have to be even by our theorem, our lemma. So what we get is then 2 divides K1 since 2 does not divide 5 by our lemma. So we knew it had to divide at least one of them. It doesn't divide 5, so it has to divide the K1. Therefore, by the definition, we have that K1 is equal to 2 times K2 for some integer K2. So that is, I'm just saying that we just said that 2 divides K1. Well, that means K1 is 2 times some integer. So we're writing that down. Now that we have that K1 is equal to 2 times some integer, we know that A is equal to 5 times K1. But 5 times K1 is 5 times 2 times K2 is 10 times K2. So what we have is A is 10 times some integer. So hence, 10 divides A. So what we've shown is the negation of the P part. So we have if not Q, then not P. And so we have, through a proof by contrapositive, shown our original theorem that if 10 does not divide A, then either 2 does not divide A or 5 does not divide A. Thank you for joining me today as we work through the proof of this theorem. I hope you enjoyed it, and I hope you learned something along the way. If you did, make sure to click that like button and to subscribe to the channel. There's more resources available in the description below, and also check out our other videos.